In this video, we look at an example from section 13.4, 13.5 on acceleration decomposition, the acceleration decomposition problem, okay? And we'll just do an example. And I'll say this is on the easier side of the examples, easier because the derivatives and magnitudes that are taken in the problem are the easy part, okay? So taking derivatives is easy and the magnitude is easy, but when you start putting those together and having to keep taking more derivatives, it leads to more complicated derivatives. So let me show you what I mean by that. Let's look at a curve R of t. It's a circle of radius 1. We're very used to this formula now. And we know that our definitions that the vector t was defined to be r prime divided by the magnitude of r prime. And n, the vector n, will also be a function of t, was t prime divided by the magnitude of t prime. Okay? So clearly to get these two formulas, you first need to find r prime. So we'll go ahead and do that. R prime is equal to derivative of cosine is negative sine, derivative of sine is cosine. There is r prime. Okay. The magnitude of r prime is equal to the square root of negative sine of t squared plus cosine of t squared, okay, which is equal to 1, because negative sine squared is sine squared plus cosine squared is 1. So from there we can tell that the vector t, okay, is minus sine of t cosine of t. Okay. To find n, we need to use this formula, okay, but n of t is t prime divided by the magnitude of t prime. So to do this, I first need to find t prime. T prime is derivative of sine is negative cosine. Derivative of cosine is negative sine. There's t prime. The magnitude of t prime, okay, will also come out to be 1. Okay, that's a nice feature. That this magnitude is so simple makes this problem easy. Okay, so the normal vector n is negative cosine of t minus sine of t. Okay, so there's t and n. They are functions of t. The entries are functions of t, which means that the vectors are going to change from point to point. Okay, they're going to change direction. Okay, very important thing to note here. Note that t dot producted with n, okay, will be sine of t cosine of t with two minus signs. Two negatives make a positive, plus cosine of t times negative sine of t. And those entries will cancel out. So t dotted with n is 0, which implies that t is perpendicular to n. So here's an example of why we know that t and n are perpendicular. Okay, so there's t and n for the circle. Okay, the next thing, remember, our goal in this problem was to do the acceleration decomposition problem. So we've now found t and n. We now need to find a sub t and a sub n, the tangential and normal components of acceleration. But to do this problem, we first need to know the acceleration. Well, the acceleration was two derivatives of the curve, or one derivative of the velocity vector. The derivative of the velocity vector is right here. The derivative would be negative cosine of t, negative sine of t. So there's the acceleration vector. Okay. And now that we have all those on the board, or on the screen here, we know that a sub t, using the fact that t and n were perpendicular, a sub t, you find it by just not solving a system of equations, but by just doing a dot product. So the acceleration vector was negative cosine of t, negative sine of t, and I need to dot product that with the vector t, minus sine of t, cosine of t. And you will see there that that comes out to be 0. Okay, so a sub t is a scalar. It comes out to be 0. Okay. In a similar fashion, we need to define a sub n. So we're just doing some computations now. We'll kind of take a look at what happened after we finish the computations. The acceleration a dotted with n. Here's the acceleration vector. Now bring in the vector n. N was negative cosine of t minus sine of t. And you'll get cosine squared plus sine squared, which will be equal to 1. Okay? So what does that say? That says that our acceleration vector is 0 times the tangent vector. The acceleration points none in the tangent direction, but it points 1 step in the normal vector direction. Okay? So we can see why that's happening if we look at our example here on the computer. Here was the curve in question, r of t. It's a circle. Okay? As you move the time around, t and n are on the left screen. Here's your velocity, and here's your acceleration in blue. This acceleration vector is what we're trying to focus on. Here are the vectors t and n on the right screen. So we're looking at how to write this acceleration vector right here on the left. How can we write it as something times t plus something times n at every time? And we can see here that since n is the same as the acceleration, that's why the acceleration is 0 times t plus 1 times n. The normal vector is always pointing in the same direction as the acceleration. Okay? So that's the circle example and a justification for this formula right here. Okay? Probably be a good, you know, and the circle is a very special example. The computations work out pretty simply. Let me take this moment to show why it is. For examples other than r of t equal to a circle, why is t perpendicular to the vector n? So we've seen that in the case of a circle, t is perpendicular to n. T dot producted with n does come out to be 0. Okay? But if your example is not a circle, you know, in the case of, say, maybe a parabola, right? We showed in a previous video at every point, right? Okay, here was your velocity vector, v. And we saw that for the parabola, a was the vector 0, 2, pointing upward. And then we know that t is the unit vector for v, and n is this vector, and it was perpendicular to t. We saw that on the video. Why was it that t and n were perpendicular to each other? It's a really nice property to have, and here's the proof for it right now. Okay, remember that t is a unit vector. Okay, that's the first step. If t is a unit vector, its length, square root of t dotted with t, which is the length of the unit tangent vector, is equal to 1. Okay, so if the length is equal to 1, then when you square both sides, t dotted with t is equal to 1. That's also true. Okay. And then I had a professor in grad school who said, whenever you had an equation that you knew, go ahead and take its derivative and see if you can see what happens. See if anything good happens from it. So I'm going to take the derivative of both sides of this equation. The derivative of 1 is equal to 0. And then we have to do the derivative here of the dot product. Okay? Well, the dot product is a product, and the derivative is a derivative, and we've showed that the derivative has the product rule property with the dot product. So if you do the product rule, you'll get t prime dotted with t plus first times the derivative of the second plus the second times the derivative of the first. And that will be equal to 0. But these are the same. Dot product is commutative. So if you reverse the order of the dot product, okay, that will still be 0. Since these are the same now, you'll get 2 of them. 2 dotted with t prime dotted with t will be equal to 0. Divide both sides by 2, right? Still 0. And then remember that you can multiply these sides by anything that you want. If you divide by 1 over the magnitude of t prime, multiply both sides by that. Okay? T prime divided by its magnitude was the vector n dotted with t has to equal to 0. Okay? Which implies that t is perpendicular to n. Okay? So there's a proof for the curves and where t and n are defined. T is perpendicular to n. And that will end this example. In the next example, we'll look at acceleration decomposition for a not so straightforward example, one where the magnitudes are a little bit more involved to work out.